going to look at how to list elements in order of their second ionization energies, right? So now we're looking at second ionization energies. This is a little bit different than the first ionization energies because we're not actually concerned with the location of our given elements on the periodic table. We're concerned with the location of the elements for which they become isoelectronic with after we've already removed one electron. So I'll show you what I mean by that. Second ionization energy means that we're looking for the energy required to remove the second electron from these elements after we've already removed one. So we're going to take one away, right? Because we're not concerned with the first ionization energy, so it doesn't matter how much energy is required to take the first electron away. We're assuming that that work's already been done. So let's figure out what these guys are going to look like after we've taken away an electron. So this row is going to be what these elements become isoelectronic with. Isoelectronic after the first ionization energy. I'm sorry, after the first ionization. So after we've already taken away the first electron. Okay. So for beryllium, after it loses one electron, it becomes isoelectronic with the element to the left, which is lithium. Lithium, after it loses one electron, right, it started with 3, it lost an electron, so now it has 2. It's going to become isoelectronic with the element moving left in atomic number on the periodic table. So if you look on the periodic table, lithium is over here already to the farthest left as we can go, so we move to the next row and it becomes isoelectronic with helium. Okay, so lithium will become isoelectronic with helium. Boron is going to become isoelectronic with beryllium, and carbon will become isoelectronic with boron. All right, so now we are going to ignore our initial elements and just look at the isoelectronic row after we've gone through the first ionization. Okay, so we no longer care what the original elements are, we just care what they became isoelectronic with. And we're going to rank these new elements in order of increasing first ionization energy, and that will tell us the order of the second ionization energy for our corresponding original elements. Okay, so how do I rank these guys? Well, remember the trend for ionization energy on the periodic table is that it increases as we go up and to the right. Lithium on the periodic table is more to the left than beryllium, and beryllium is more to the left than boron. So we would expect that we would expect that lithium would be less than beryllium, and beryllium would be less than boron. So I'll write that over here. We would expect lithium to be less than beryllium, and beryllium to be less than boron. So where does helium come into play? Well, remember, the ionization energy increases as we go up and to the right, and the most up and to the right as we can possibly get on the periodic table is helium, right? Because there's nothing more up and more to the right than helium on our lovely periodic table. So helium is the maximum ionization energy, so of course it's going to be greater than everything else. Now this is what we would expect if we simply followed the trend, but of course there is an exception here. And that exception occurs between beryllium and boron. And in order to understand this, we have to go to the electron configuration for both of these elements. The electron configuration for beryllium is pretty simple, right? It's just 1s with 2 electrons, and then 2s with 2 electrons. the electron configuration for boron is pretty simple as well. It's just 1s with 2 electrons, 2s with 2 electrons, and 2p with 1 electron. Now, if we remember from chapter 6 how energy levels work for electrons, it becomes pretty clear why the ionization energy of beryllium will be greater than boron. Because the outermost electron in boron is in a 2p orbital, whereas the outermost electron for beryllium is paired in a 2s orbital. Okay, so which of these is higher in energy, the 2s or the 2p? Well, that's a little bit difficult to answer because we would have to know how many protons are in the nucleus, because the energy of the orbital is going to be affected by the effective nuclear charge. But it turns out that actually the additional energy from the 2p orbital in boron is enough to overpower the additional attraction to the nucleus by the additional proton compared to beryllium. So the net result is that this electron in boron is easier to remove than the 2s electron in beryllium. Therefore, the ionization energy of boron is less than that of beryllium. Remember, ionization energy is a measure of how much energy you have to put in to take these electrons away from the atom. So if it's easier to remove this electron from boron, that means we have to put in less energy to take it away. Therefore, boron has a lower ionization energy than beryllium. So if we go back to our analysis, we'll make the correction here that our final answer will be lithium is less than, well, not our final answer, but closer to our final answer. Lithium is less than boron, is less than beryllium, is less than helium. And the last thing to do would be to go back to our original elements and remind ourselves what these guys came from, right? Remember, these are the isoelectronic elements, but we want to go back to our original elements. So lithium came from beryllium, boron came from carbon, beryllium came from boron, and helium came from lithium. Now you'll notice that the second ionization order didn't really have anything to do with our original elements. It had to do completely with what those elements became isoelectronic with after they lost their first electron. And that's the key for doing second ionization energies.